Okay, so this question is to use the frequency sampling method to find the filter coefficients. Okay, so the idea is, so first we draw the frequency domain diagram for the filter, okay, for the ideal low-pass filter, and then we take a sample of that filter, so get the discrete Fourier transform. Then we do an inverse DFT. We can find the time domain expression, which is the filter coefficient. Okay, first step is we want to draw the frequency domain representation. For example, this filter have something look like this. Its cutoff frequency is 5, okay, 0 to 5 hertz. The sampling frequency is 18, okay, so this is 2, 4, 6, 8, 10, 12, 14, 16, 18, okay, so this is 18. Let me write it down. Sorry, this is 6, 8, 10, 12, 14, sorry, something wrong here. So 18, right? So because the sampling frequency is 18, so the frequency domain representation will, mirrored symmetrical against 9. Okay, so this is 8, this is 10, this is 6, this is 12, this is 14, this is 16. Okay, sorry about the drawing, it's not really in scale, but this is 0 to 5. Okay, so this is 13, start from 13 against symmetrical against the 9. So we're gonna take n sample of this. The sample is the filter length 9. Okay, so n equal to 9. We're gonna take 9 samples. So the frequency sample is look like this. So the frequency sample at k fs over n. Okay, so each n is 9, so 18 is kilohertz. So we got this one got a kilohertz, that's the unit. So we're gonna take at 0, at 2, 4, 6, 8, 10, 12, and 14. So these are high, or 1, okay, and 16. So 5 on the top, 4 at the bottom is 9 in total. Okay, so in this case, this horizontal axis, instead of a frequency, this was a frequency. This time it becomes a k. Okay, become index. So the index start from 0, 1, 2, 3, 4, 5, 6, 7, 8. 0 to 8 in total 9 points. Okay, so k is the index, so use that we can find exactly the sample frequency. So we got the HK frequency domain representation for that. So HK equals to 1 when k equals to 0, 1, 2, 7, 7, this one, right, 7 and 8. Okay, for the other, well, k gonna equal to 0, 1, k equals to the other 3, 4, 5, 6. Okay, so that's the HK, capital HK in frequency domain. Okay, So we're gonna give a number for that as number 1. So what we're gonna do is we want to do we will do a inverse DFT for that one. Okay, if you can do that, then we can calculate. So the inverse of the capital HK, then we will got the lowercase hn. Then we plug in n equal to 0, 1, 2, 3, so we can got all the coefficient. Okay, so that's the idea. So hn gonna equals to 1 over n, so that's the definition for inverse, definition for the inverse DFT. Okay, I will put it down here. So HK is this one, and e to the order of j 2 pi over capital N, and lowercase n is this index, and capital lowercase k, which is the index for this sum. Okay, so this is equation number 2. Okay, so we're gonna derive the one of the equation from the lecture slides. So in the final version, we're gonna start from here, and we're gonna go all the way to get this conclusion hn equals to 1 over n. Start from sorry, it's not that one. So 1 over n, the sum of k equal to 0 all the way to n minus 1, and the magnitude of hk, okay, cosine, what is that, cosine 2 pi k over capital N, n minus 1, 2 over 2. Okay, that's something you got from the textbook or from the lecture slides. This equation is true for the linear phase. For linear phase FIR filter. Okay, linear phase FIR filter with positive symmetry. Okay. So if you don't want to see the proof, you can just jump to the later section of this video. Otherwise, we're gonna prove that. Okay, we're gonna prove that. So based on Owen's notes, so on table 6.1, you will find that capital HK actually equals to the magnitude of capital HK multiplied with e to the order of negative j omega capital T with capital N minus 1 divided by 2. Okay, that's the equation number 3. So for those conditions like linear phase and positive symmetry, then we got HK equal to those. So what we're gonna do is we're gonna plug in number 3 into number 2. Okay, number 3 equation into number 2. Then we got capital HN equals to 1 over n sum k, start from 0 all the way to n minus 1, and we just copy down this capital HK e to the order of negative j omega t, n minus 1 over 2, and then that's replace the HK here, and don't forget to multiply e to the order of j 2 pi over n k. Okay, so I'm gonna replace something. So there is omega, and we also know that the sampling at a frequency. So we're sampling this at a frequency f equals to a kfs over n. Okay, that's how we sample the frequency spectrum. So the omega gonna equals to, because omega equals to 2 pi f, right? So omega over 2 pi, that's just the f equals to k over n multiplied with a t. So 1 over t is just fs, right? So the t is the period. So we got omega equals to k 2 pi over capital N and t. Okay, so where you know that capital T is 1 over fs. Okay, so can keep doing that. So let me shrink that a little bit. So we got then we're gonna just collect terms and change things. So the hn equals to 1 over capital N, the sum k equal to 0 and minus 1, then capital HK, the magnitude, e to the order of negative j. Here we got something changed. So you can see the omega here. We're going to change that omega. We're going to change that omega. Okay, see that the omega here. We're going to change that with this one we just derived. K 2 pi over capital NT. Okay, then we got the rest. We got the t, we got the n minus 1 over 2. Okay, so we can make some changes here. So this t gonna be cancelled. Okay, and we're gonna multiply with e to the order of j 2 pi over n, multiply with a lowercase n and a k. Okay, so we just changed the omega here because they are multiplied together, and you can see here's a 2 pi over n, here's a 2 pi over n. Then we can take the j 2 pi over n out. This one become a negative n minus 1 over 2. This one, what's left is just an n. Okay, oh sorry, we can take the k out as well. So the next line, we just copy down these the front matters, just copy them down. HK magnitude e to the order of, here's a k, here's a k as well. So we got this j common term, 2 pi k, okay, 2 pi k over capital N. So 2 pi k over capital N. So n left, lowercase n is from here, and this minus sign here, capital N minus 1 over 2. Okay. So here is, need some more space. Let me move this one. So this term, we're gonna use the Euler equation. Okay, so the Euler equation, we can extend it into a cosine and a sine term. Just use that equation. So it's gonna become a pretty long equation. So this one equals to 1 over n sum k equal to 0 and minus 1 and h k capital magnitude, and this one becomes cosine 2 pi k over capital N lowercase n minus 1. All right, this n is really not very good. So n minus 1 over 2 and plus a j sine, same thing, 2 pi k over capital N lowercase n minus 1 over 2. Okay, so we're gonna have two terms, and because Hn is a things as Hn lowercase hn are real value is real. It's real. Okay, so sine term, this sine term, because the sine term comes with a j here. Okay, the sine term must equal to 0. So we just proved, let me copy down what we got here. So we just got this one. Okay, so this is where you got the equation from the textbook or from the slides. So here we go. After that, we can start to calculate n equal to 0 all the way to 9. So for 8 for these 9 terms. Okay, so we know that capital HK, so the magnitude is symmetrical about, so it's a symmetrical about Fs over 2. Okay, that's the sampling property, and you can reduce the calculation. We can just calculate half of it. So this Hn, we can just equals to 1 over n. So we can reduce that from k equal to a 1, because we're going to have a k equal to 0 for a separate term, and n minus 1 over 2. So we can only calculate half of the term. So this one is double of that because they are symmetrical. So HK cosine, because you are sum them, so the first half and second half the same, so we can just double the magnitude. 2 pi k over n, and this is n minus 1 over 2 plus a capital H 0. Sorry, we didn't start from a k equal to 0. Here we put the k equal to 0 here, so capital 0 is a k equal to 0. Okay, so that's the general equation for Hn. Okay, so we start all the way from capital HK and do the inverse DFT, and we simplify and change it to this form. Then we can start to, so the difference I want to highlight here is the range here is different, okay, and here is a 2 as well, and there is another term. Okay, so next we're gonna plug in numbers. Also, we find the positive symmetry of Hn. So because of the positive symmetry of Hn, this actually means that H0 just equals to H8. So n equal to 0 and n equal to 8 are the same. Another thing is H1 is equals to H7. So H2 equals to H6. 3 equals to 5, and 4 equals to, of course, 4. Okay, so then we can start to calculate those for let me put this one aside so it's not really affecting the calculation. Then we got HAN equals to these. We can plug in some common numbers, so we know that n equal to 9, so 1 over 9. Okay, sorry, and we know that the k, so we can start from k equal to 1, so 9 minus 1 is 8, so up to 4 terms. So 2 multiplied with capital HK, they are different values for k equal to different number. Cosine, here is a 2 pi k over a 9, and n minus a 4, and plus capital H0. And we all know how much is a capital H0. H012, capital H012, we all know that because we actually have that numbers, right? So we remember that there's a 4 there, another, let me scroll, reduce it a little bit. Okay, so we got 2, so that's the value we already know. Okay, so let's plug in numbers. So H0 is just equal to 1 over 9. So we're gonna sum all the terms, right? So for k equal to 1, which is what was that? 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, k equal to 1. So we got a 2 multiplied with HK H1, okay, and multiply with the cosine 2 pi k equal to 1 over 9, and n equal to 0. Okay, for this case we got so we got n equal to 0 for this particular calculation, and k is looping around between 1, 2, 3, and 4, right? 1, 2, 3, and 4. So n is 0 here, so it's a negative 4. 0 minus 4 is negative 4, so it's a negative 4. And that's k equal to 1, right? So this is a k equal to 1. And h1, you can see here, h1 is a 1, right? h1 is 1. So we know this one equal to 1. And we're going to plus 2, right? So 2 multiply with a capital H2. And we know H2 is also 1, right? And cosine 2 pi multiply with a 2, right? K here is 2 over 9. Again, 0 minus 4 is negative 4. Okay, so the next term is for k equal to 3. For k equals 3, we don't need to care much because capital H3, capital H4, okay, these all equal to 0, right? Because these are equal to 0, so this term are equal to 0, they all will be gone. So we only have H1, H2, of course we got a H0 as well. So we're gonna plus a 1 here, right? So that's all for this first term. So you're gonna plug those numbers in, use your calculator, then you will find this number equals to 0.0725. Okay, this also equal to H8. Okay, for the positive symmetry. Let's do another one so you can see the pattern. So H1 in this term, in this time, n equal to a 1. Okay, so 1 over 9 again, and then we got this 2 multiplied with H1, which is 1. Okay, cosine 2 pi over 9, and here is 1 minus 4 is -3 instead of -4. Okay, and plus a 2 multiplied with h2, which another 1, and cosine 2 pi 2, because k equal to 2 over 9, -3. Okay, and plus 1 for h0. Okay, these are the capital H0. And again, capital H3 and H4 are equal to 0 because these terms, so we don't have that terms. So for that, this H1 equals to -0.11 is equal to H number 7, lowercase h number 7. Okay, so you're going to do this for H2. I will not write the full version, is equal to -0.05912. And this one also equal to H6, then H3 equals to 0.3199, and this one equals to H5. Okay, and for H4, it's a bit interesting. So 1 over 9, let's do that. So 2 multiply with a H1. Okay, H1 is 1, so we just neglect that. 2 pi over 9, and this time is a 4, n equal to 4. Okay, 4 minus 4 is 0. All right, so this is simplified as well, and plus a 2 cosine 2 pi 2, which is a 4 pi over 9, and another 0, and a plus 1. Okay, this one equal to 0.555. So yeah, so from h equal to 0 all the way to h equal to 9, we got all the parameters.